Hello and welcome to this section of the Calculus 1 Derivative Help Tutor. In this section we're going to talk about what we call related rates. It's a fancy sounding name, and what it really means is word problems in Calculus 1, or word problems with derivatives, really is what it is. And I'm not going to lie to you, most students find related rates one of the toughest topics in all of Calculus 1, definitely related to derivatives. Because what you have here is a bunch of word problems. Every one of these things is going to be a word problem. So you'll have to read it, you'll have to be able to draw a picture or set up some kind of diagram or something so you know what we're talking about. You have to identify what we know and what we're trying to solve for, and then you'll have to write an equation on your own. It's not going to be given to you. You'll have to write your own equation that describes the situation, and then use all of the techniques of calculus that you've learned to this point to solve the problem. So there's 4 or 5 different links in that chain that if you don't get one of those links correct, or if you're not comfortable with one of them, then you're going to bomb this section. If you don't know how to read a problem correctly and set up a diagram, you'll bomb this section. If you don't know how to write an equation that describes it, you'll definitely bomb it. If you don't know how to take derivatives and what all that stuff means and solve equations, you're going to bomb it. So there's really a lot of things here, but I want to give you a little bit of a pep talk before we get started. In that a lot of students will read these, you'll watch these things and you'll say, well, okay, I kind of get that, but I never would have figured that out on my own. A lot of students will say that when they watch these problems. They'll say, well, I kind of follow that, but I never would have figured that out on my own, and they'll feel hopeless. You need to make a conscious effort not to beat yourself up if you don't understand and you don't see the path to the end of the problem ahead of time. Heck, when I work these problems the first time, I don't see the end of the problem. I don't see start to finish how I'm going to get there. I just start writing things down that make sense, and then I can eventually see how I can solve it. It's like you don't do a puzzle, a jigsaw puzzle, all at one sitting. I mean, you place the pieces of the border and then you piece things together and you finally get to the end. Same with this. You write down what you know and you make your way to the end. You don't see the entire solution in your head. You just can't do it. The other thing is, once upon a time in 3rd grade when you were learning regular word problems, like, Jenny goes to the store and has $5 and somebody gives her $5 more. How many dollars does Jenny have? Well, you know that that's 5 plus 5 is $10. But once upon a time, you didn't know that. It wasn't so clear that when someone gives you more money, the word more tells you that you're going to need to add those together, because you were just learning how to interpret those words, all right? How did you figure it out? How did you get good at that? It's through practice. You worked a ton of those problems, and eventually you figured out that when somebody gives you more money, then that means you're going to add them together. How many more socks do I have than John? When I say how many more do I have, it means I'm going to subtract those things generally, right? That all comes through practice. So when you look at these related rate problems, the first few of them, you might look at, you might say, boy, I get it, but I don't think I ever would have figured that out on my own. But you need to realize that the process to get good at these comes from doing them. It comes from seeing these problems. So if you see 10 of these problems, and then you work your 11th problem, you're going to get the hang of how to set it up just by the fact that you've done it before. You're going to get the hang of how to set them up because you've seen how it was done before. So if you don't see the first, if you kind of get it but you don't quite feel like you would have done it yourself, don't worry about that. Just get good at these problems that I'm going to present to you. And when you get on your test, you'll have a very good starting methodology for you to get to the end. Okay, so let's begin. The first problem says, the radius of a spherical balloon shrinks at 1/2 meter per minute. How fast is the volume decreasing when the radius is 4 meters? All right, so we have the radius of a spherical balloon. It's decreasing, it's shrinking at 1/2 meter per minute, so it's going down like this. How fast is the volume decreasing when the radius is 4 meters? There's a lot of context clues here. But the number one thing you need to do is draw a picture. I cannot stress it enough. Every related rate problem you have, you must draw yourself a picture. The second thing is, what are you going to draw a picture of? We have a spherical balloon. That's a huge clue. So let's draw ourselves a sphere. Right? So here we have a sphere. So we know we're going to be dealing with a sphere. That's a huge clue. It doesn't tell you what to do with that information, but it tells us that we have a sphere. So this sphere in general is going to have a radius r. All spheres have radius r, right? So we can label this ourselves. And when we read the problem, the radius of the spherical balloon shrinks. So this number is going to be shrinking eventually, right? And it gives us the rate. How fast is the volume decreasing? So we know that we're going to be talking about volume. So what is the formula from geometry of the volume of a sphere? V is equal to 4/3 pi r cubed. Now here is your first clue. When you look at the problem, it talks about the radius of the balloon shrinking. Then it also talks about the volume of the balloon. So when we pull from our head, what relation can we come up with that talks about the volume of a sphere? This is the only one that is basically available to us. And the volume of a sphere is related directly through this exponent here. It's related to the radius. So both of the quantities that are talked about in this problem, the radius and the volume, are described by this equation. That's a huge clue that you're on the right track. I can't stress it enough. It's pretty obvious here because we have a spherical balloon. But later on when you have some different problems, you need to pick a relation, something that involves the variables that the problem is talking about. Because we're going to take the derivative here in a minute, and then we're going to be plugging in numbers that were given from this problem, so we need to have an equation that makes sense. All right, so step number 1, draw a picture. Step number 2, write a relation that relates at least some of these variables together. Step number 3, we need to begin to label some of these things. So it says, the radius of this balloon shrinks at 1/2 meter per minute. So when we say shrinks at 1/2 meter per minute, what does that mean? That's a rate of change. That's how fast the radius is changing. That is a derivative of the radius with respect to time. And you can tell just by looking at the units that it's a derivative, meters per minute. dx divided by dt, that's meters per time. That's unit of length per unit of time, meters per minute. So you can tell right away that that's a derivative. They're trying to give you in words a derivative. What derivative is it? The radius of the balloon shrinks. Well, the radius shrinking would be dr dt. And it shrinks at 1/2 meters per minute. But notice it's not growing larger. It's actually getting smaller, so we have to put a negative here, right? So what this is given. This is not something we're deriving. This is straight out of the problem. dr dt, the rate of change of the radius with respect to time, is negative 1/2. And if it makes you feel better, it's always a good idea to put the units out here, and you can put meters per minute. And that reinforces that it's units of length per unit of time. It doesn't matter meters per second, kilometers per hour. It doesn't matter. They're giving you a rate. The unit is in meters per minute, and this is what it was given to us as. Now the next thing is we need to pull out of this problem what we're trying to find. How fast is the volume decreasing? That is the question. How fast? Anytime you're given how fast or what is the rate of, that's a derivative. How fast? Think about it. That's how fast. That's the rate of change of the volume with respect to time. When you say how fast is something, right? So what we want is, let's just write it out here. We want dv dt, the rate of change of the volume of the sphere as it relates to time, is equal to question mark when, and I write it just like this, when the radius is equal to 4 meters. So we have the same consistent unit, meters and meters. So all of this stuff that I've written down on the board so far is given. We've really solved absolutely nothing. But you see what I'm saying? When you were in 3rd grade, you were given these word problems about milk and candy bars and money and going to the store. And you had to read a ton of them to understand what you were being asked and what you were being given. That's a huge skill when you're younger. Well, when you're doing word problems in calculus, you have to learn those skills again, but using the knowledge of calculus. So you see, you have to know you're talking about a sphere, so you have to pull this function out because you know that's going to be related. You're talking about the rate of change of the radius, so you have to know that that's going to be dr dt, and you have to know that it's negative because it's decreasing. If it were increasing, then dr dt would be positive, be getting bigger. And then you have to look at what the problem's asking. It's asking for dv dt. It's equal to something when the radius is 4 meters. So let's say this balloon starts at a 10 meters radius, huge balloon. It's decreasing at this rate, 1/2 meter a minute, right? So it's decreasing. Well, eventually the radius is going to get to 4 meters. So it's going to get to 4 meters. At that moment that it gets to 4 meters, how fast is it? How fast is the volume of that guy changing? So all of it is related by this equation up here, by the volume of a sphere. So we have the volume of a sphere, how are we going to proceed? Well, we have all these derivatives everywhere. So it's a pretty good idea to go ahead and take the derivative of this equation, because that's going to introduce all of these other derivatives that we know we have the values for. So it's 4/3 pi r cubed. Now, this is a function, really, v as a function of the radius r. But none of these derivatives are with respect to dr. They're all with respect to time, because it's all velocity based. So what you really want to do is take the derivative of both sides of this equation with respect to time. And so you don't have time anywhere in this equation. You have v and you have r. So you need to use implicit differentiation. That's why we learned about it in the last section. So let me go ahead and do that, and then we'll make sure you understand. What is the derivative of the volume with respect to time? We don't really know, so we just write dv dt. We're taking the derivative with respect to time of both sides of this equation. All right, 4/3 pi is just a constant, so it just stays out front. We don't have to do anything with that. Now we have r, but we're taking the derivative with respect to time. So because it's not, we're not taking it with respect to r, the way we handle it is just like in the implicit differentiation section. We take the derivative of this guy just like we normally do, 3r squared, but then we have to multiply by dr dt. This is incredibly crucial for you to understand this, because you're going to see this a lot. We want to take the derivative of this guy with respect to time. So we want to know, well, how does the volume change with time? So we write that down. These are constants, so they come out. When we take this guy, basically what you're doing is you're sort of like using the chain rule. 3r squared times the derivative of the inside. The inside is just r, so you make it dr dt. There's lots of different ways you can think about it, but ultimately when you take the derivative of an equation, and you don't even have your variable in here anywhere, then when you take the derivative of it, you need to put a dr dt, the derivative that you're taking the derivative of the inside term, which is r, because by the chain rule, that's basically going to get you where you're trying to go. And if you remember back to the last section in implicit differentiation, when we had y's and x's everywhere, when I said, well, when you get to a y function, take the derivative normally and then say, well, dy dx, because we're trying to take the derivative of with respect to x in the last section. And I told you, we don't know how y changes with respect to x, so we have to tag it and multiply it by dy dx, because that would be the full derivative. Same exact thing here. We take the derivative of this normally, but we don't know how r changes with respect to time, so we have to multiply by it. All right? So this is the derivative of this function with respect to time. Now notice what we've done. We've got this guy, and what we do here is this 3 is going to cancel with this 3. So what we're going to eventually have is dv dt is equal to 4 pi r squared dr dt. Now look at what we have. Let's see what we're given. We're trying to find dv dt, right? But we want to do it when the radius is 4 meters. We can put the radius of 4 meters in here. This is a number, this is a number, this we know. dr dt is given to us by -1/2. So we actually know everything on the right-hand side of this equation. So dv dt is equal to 4 pi. The radius is 4, so we'll do 4 squared. This derivative is -1/2. Right? So what you're going to have is 4 pi 16, and this is going to be -1/2. So then just continuing to do the math, what we're going to have is we'll have 2 divided by 16 is going to give us 8, and then 8 times 4 is 32, so we'll have -32 pi. So that's dv dt. So this is the answer, but try to relate it back to units. If this is how much volume is changing with time, what would the units be? Well, up here in the original problem, the unit of length that we were using was meters. The unit of time that we were using was minutes. So if this is a volume change with respect to time, the unit is going to be meters cubed per minute, because we have to have the same units as what we started with. That's what defines and locks down the units to begin with. So it's -32 pi meters cubed per minute. Notice we have a negative sign. What does this mean? What is the physical meaning of a negative sign on a derivative? It means it's getting smaller. If it were positive, it would mean the volume as it changed with respect to time would be getting larger, but of course it's not, because we know the radius is getting smaller, so the volume is going to be getting smaller. So this means it's decreasing. So you see everything's consistent. The radius is getting smaller as a function as time goes on, so therefore the volume is getting smaller as time goes on. So let me go through it one more time. We lock down an equation that relates the volume and the radius. We write down everything that we know. We take the derivative of both sides. When we take the derivative of the left-hand side with respect to time, basically we just get dv dt, because that's what it is. We take the derivative of volume with respect to time, there it is. These are just constants, so they stay out here. When we get to the radius r, we take the derivative normally, but then we have to tag it with a dr dt because we don't know how r changes with respect to time. All right, and then we cancel terms, and we're left with this guy, and then we notice right away that we know everything on the right-hand side, so we just plug it in, find the answer, write our units down, consistent with the units that we started out with. Now, it's an excellent first problem for related rates because it teaches you what we're doing without getting too complicated. Some of the problems down the road are going to get a little more involved, because this was fairly simple when you look at it, because once we took the derivative, we knew everything over here very, very rapidly because it was all given to us. But fundamentally, though, you're going to follow the same procedure for all of these problems. You're going to write down what you're given, and you're going to draw a picture, and then you need to always find some equation that relates some of these variables together, and then you're going to take a derivative, and then you're going to plug in what you know, and you're going to get the answer. But the trick is labeling what you know, and label what you don't know, and label your equations in your drawing, and so there's a lot of chances for error in there, but that's what you're going to do every single time. All right, so let's go and do the next problem and get some experience here. Water leaks onto a floor and creates a circular pool with area that increases at a rate of 3 square meters per minute. How fast is the radius of the pool increasing when the radius is 10 meters? So we have water being poured basically onto a floor, and it's making a circular puddle that gets bigger and bigger, and we're told that the area the area of this circular puddle is increasing at a rate of 3 square meters per minute. So let's start to draw a picture at this point. So let's just sort of, pretend I have some water rushing onto a floor or something like that. And basically I have this sort of circular puddle that's formed. It's getting bigger and bigger and bigger. Right? So this circular puddle obviously is going to have a radius associated with it, like this. The reason I picked this picture is because it tells us I have a circular puddle, right? Now notice that it's a circle. That's a huge clue. And we're talking about the area of the circle is increasing. So that should be an immediate clue that I'm going to be using the area of the circle. Area of a circle is pi r squared, right? So I have the radius here, and I'm solving, I'm involving the area. All right? So the area is increasing at a rate of 3 square meters per minute. When I say the area of something is increasing, just like in the last problem I told you, that's a keyword. Just like milk in the grocery store back in 3rd grade, you had those keywords. When you find something is increasing or decreasing in calculus, it's an instant keyword for derivative. Because when something's increasing, it's changing in a larger sense as time goes on. When it's decreasing, the rate of changes is getting smaller as time goes on. So the thing is getting smaller as time goes on. Here, the area is changing at a certain rate. So what this means is that this is given to us. dA dt, the derivative of this area with respect to time, is a positive 3, and the units are meters squared per minute. This is all given to us in the problem, but it's up to you to tag it and tell yourself that it's equal to dA dt. The rate of change of the area of this puddle is increasing at a rate of 3 square meters per minute. And this is a unit of length per time. This is a unit of length per time. So everything is totally self-consistent. Now the other piece of information, after we're given that, how fast is the radius of the pool increasing? So that's it right there. How fast, that's derivative. How fast is the radius of the pool increasing? So the radius, how fast? So dr dt is equal to question mark. I don't know what it is. That's what I want to know. When the radius is equal to 10 meters. So this is sort of like, almost like we set the last problem up. This is everything that was given to us. So it's your job, when you're doing a related rate problem, to draw yourself a picture, find an equation that relates the variables, write down the derivatives that are given to you, and even sometimes you have things that are not derivatives that are given to you. But you have to write it all down. If you just try to solve the problem without doing that, you're never going to get it right. You're going to be going in circles because you won't know where you're trying to go. Here I know I'm trying to get to dr dt. So I'm going to start with this equation up here, the area is equal to pi r squared. It seems like a pretty good idea to take the derivative of this equation, because then I will get dA dt, which I know. I will also get dr dt, which I'm trying to find. So I'm going to do that. Take the derivative of both sides with respect to time, because I'm dealing with these rates. So on the left-hand side, the derivative of area with respect to time is just simply dA dt. I don't know what it is. So I'm just going to write dA dt is equal to. This is just a number, pi, so I'll leave it out in front. When I get to this radius, I take the derivative of it normally. So it'll be 2r, but then I have to tag it with dr dt because I don't know how the radius changes with respect to time. Right? Now the other thing I'll say is this is all self-consistent. On the left-hand side, I'm telling you, well, just take dA dt because you don't know what the area is with respect to time, so you just write it down. But you're doing the same thing. If this were a variable, it is a variable, what would be the derivative of a? Or the derivative of x? Just think back to the first section of Calculus 1. The derivative of x, what's the derivative? It's just 1, because you've got a coefficient out here of 1, power of 1, so you bring the coefficient down, a to the 0 power, so you're just left with 1. So really when you take the derivative of the left-hand side, you're doing the same thing that you're doing here. You're saying the derivative of this is 1, but I have to tag it with dA dt because I don't know how this area changes with respect to time. And over here I'm doing the same thing. I'm taking the derivative 2r, but I'm tagging it with dr dt because I don't know how it changes with respect to time. And going back to the previous problem, when I take the derivative of this volume, the derivative of just v is 1. But I have to tag it with dv dt because I don't know how it changes. The derivative of this is 3r squared, but I don't know how dr dt relates, so I put dr dt. So you're doing exactly the same thing to both sides. You're taking the derivative of all the variables and you're tagging it with dv dt, or or whatever variable you have, dt, because that's what's going to give you what you need. So just to tidy it up a little bit, dA dt is equal to 2 pi r dr dt. Now let's look and see what we have. I'm trying to find dr dt, okay, that's okay. The radius I'm given at 10 meters. dA dt, the rate of change of the area I'm given, and everything else is a constant. So actually I know everything. dA dt, the rate of change of the area is 3. 2 pi, the radius that I'm looking at is 10 meters, and I'm trying to find dr dt. Now don't forget what this sentence really means. You start with a small puddle, the water just flows. It's getting larger and larger and larger. Eventually you're going to get to a radius of 10 meters. Once the radius hits 10 meters, at that exact moment, that is the moment you want to know what the rate of change of the area is. How fast is the area increasing once you get to that exact point? That's what that piece of information is telling you. So we've got everything plugged in, and so it should be a simple matter. dr dt is equal to, well, I have 3 on the top, 2 times 10 is 20 on the bottom, pi. So I just take all this stuff and divide over, basically, 3 over 20 pi. What is the unit here? Well, I've got dr dt, that's a unit of length and a unit of time. So this is going to be meters per minute. The reason it's meters per minute is because my original problem was defined in terms of meters squared per minute, so my unit of length is meters, my unit of time is minutes. You have to be self-consistent in the units. So what this means is that you start with a small puddle, right? You turn the water on, you barely start a puddle, and it gets larger and larger and larger, right? So what this means is that once the radius hits 10 meters, at that exact moment, what we've solved for is how rate of change of the radius is equal to this number, you could get a decimal for it, meters per minute. So you might imagine that it's going to go out like this, and when the puddle is small, you might have a very rapidly increasing radius. Maybe the radius gets small, the rate of change of the radius gets smaller and smaller and shorter as you get out because you have a much bigger circle. So what's basically happening is when you get to 10 meters, you want to know how fast is the radius changing once you hit 10 meters. That's what this number is. The problem also tells us that the area is changing at this rate at that time as well. But notice the process is exactly the same. Draw a picture, find an equation, write down what's given to you, take the derivative, usually using implicit differentiation, and then plug in what you know. And this process, I'm starting out with some easier problems, but the process is basically going to be the same. Now for the next problem, I want to draw something first before I actually read the problem to you. So right here I have a wall, that's what the shaded area is, and the horizontal part is the ground, and I have a ladder like this, right? And the ladder is 13 meters, Okay? Now this is something you might see in your textbook. So this is a ladder leaning up against the wall. And the problem says, suppose the top of a ladder is pushed up a wall at 1 meter per second. How fast is the base of the ladder approaching the wall when it is 3 meters from the wall? Okay, so you really have to look at this. If you're pushing up with 1 meter per second, that means you grab this and you drag it up the wall. So this base is going to scoot towards the wall at some speed, right? So I'm pushing this guy up at a certain speed. This is going at a certain speed. And I want to know, once I'm at 3 meters from the wall, like about here, then how fast am I approaching the wall? Without calculus, it would be super difficult to even figure out how to approach this problem. But the thing that you need to do here is, this problem is what you would typically be given in your book. What you need to do is redraw this problem and label it, because you're going to need to introduce some labeling a lot of times. So let's redraw it. And the only reason I'm redrawing it, you'll see, is the following. So we'll put 13 meters here again. All right. And what you need to do is you need to make some labeling here. So let's call this the x dimension, and let's call this the y dimension. The reason we have to do this is because in the previous two problems, when we had circles and spheres, we have the equations for those already. V is equal to 4/3 pi r cubed. You know, A area is equal to pi r squared. So those are already locked down and defined. For this guy, if you ever have a hope of writing an equation that you can take the derivative of, you need to invent some variables and put them on your diagram. That's not going to be done for you usually. It was done for you in the original problems because your circles and spheres are pretty easy with radius and volume and area. But here, nothing is labeled except for the length of this ladder. So you need to have something to be able to put on there to measure these distances, right? So label something, you can call it, I don't care, alpha, beta, it doesn't matter, but let's call this x and y because that makes sense from the coordinate plane. Now once we have that labeled, let's go write down what we know. The top of a ladder up here is pushed up with a speed of 1 meter per second. Notice it says at a rate of 1 meter per second. That's a huge clue for a derivative. Meter per second means rate of change of position, right? So what it means is, in math, dy dt is equal to 1. And the unit is meters per second. Length per time, positive 1 because I'm going positive up this way. So you see how it was important for us to label our diagram, because if we didn't label it, we wouldn't be able to write the derivative down. So you have to have some variables in order to write your derivatives down. Now, what we're trying to find is how fast is the base of the ladder approaching the wall. That is dx dt. How fast means derivative. How fast is the base of the ladder approaching the wall? That's a big question mark, I don't know. When, and it says when it is 3 meters from the wall. That means when x is equal to 3 meters. So when this value shrinks to 3 meters, how fast is the base of that ladder hitting a wall? Now we are in a position to do some work, because we have everything done that we said we needed to have done. We have a drawing, we have variables, we have derivatives labeled based on our problem. Now one more thing remains. What equation can we use to make some progress? Well, when we were dealing with the sphere, we had 4/3 pi r cubed. When we were dealing with the circle, we had the area pi r squared. What equation can we use here? Ultimately, we're trying to find an equation that relates x and y, because these are the derivatives I have. So look, you have a right triangle here, and we know the hypotenuse, right? It's 13 meters. So what you really have is x squared plus y squared is equal to 13 squared. This is just the Pythagorean theorem, right? This is an equation that relates x and y together, without any problem. So what we need to do is take the derivative of this equation, because then we'll have derivatives of x and y, which we actually know the values for. So let's do that. Let's take this with implicit differentiation. We look at this. Notice we're taking the derivative with respect to time, because that's what we have the values for. So you take the derivative of this normally. It'll be 2x, but you have to tag it with dx dt, because we're taking the derivative. We're not taking this derivative with respect to x. We're taking it with respect to a wholly other variable, the value with respect to time. There's no time anywhere in this stuff. So we want to know how x changes with respect to time. So you take the derivative of the function as a whole, multiply by the derivative of the inside function. In this case, is x, so you just tag it dx dt. Okay? Plus, take the derivative of this, 2y, times the derivative of the inside, but that's dy dt. the inner function here, so to speak, is y. The inner function here, so to speak, is x. So when you take the derivative of the inside, it's just dx dt. This becomes dy dt. On the right-hand side, you just have 13 squared, but you're taking the derivative of it, so you get 0. Okay, you get 0. So now we are almost to the point where we can solve this problem when you really look at it. What we are trying to find is dx dt, this guy right here. So we're going to solve for this. And the other thing we know the value of is dy dt. That's given to us by 1. All right. We also know what x is equal to. That's 3. So let's go ahead and try to solve this problem here. So let's go ahead and put a 2 in here. X is equal to 3, so we'll put it in there. Dx dt is what we're trying to find, so let's just leave it dx dt. Plus 2 times y. Well, y is this value here. I don't know what y is, so I'm just going to leave it sort of blank for a second. But dy dt is just 1, is equal to 0. So what I'm trying to find is dx dt. That's what I'm trying to find, but I have everything in this equation except for this value of y. So I'm thinking I'm stumped. I'm like, man, I really thought I was on the right track, but I'm stuck because in the other problems, we just plugged in everything we knew and then bam, we had the answer. But here, obviously, I don't know the value of y. But if you think carefully, you'll realize that you actually have enough information to find what y is because this is just a Pythagorean theorem. So when x actually gets to the value of 3 meters here, this 13 meters always stays the same, so I can calculate y. So what I'm going to have is x squared plus y squared is equal to 13 squared. This is always true, right? X, I'm going to eventually get down to a value of 3, so it's going to be 3 squared plus y squared is equal to 13 squared, which is 169. So this is 9, so when you subtract it, you'll get y squared is equal to 160. Right? That's what you're going to get. And then when you take the square root of this guy, what you'll eventually find out if you do a factor tree is you'll get 4 times the square root of 10. What we have found is that at the moment that this ladder gets 3 meters away from the wall, at that moment, the height of the ladder against the wall is this value. Now you can convert to decimal, but you should have figured out by now in calculus you don't convert to decimals. Leave everything exact. That's how your professor's always going to want it. So this is the value of y that is true once we get to a value of x is equal to 3. So we just put it in there, 4 times the square root of 10. Okay, now we've basically got everything we need to find the answer. So what we'll have is 6 dx dt plus 2 times 4 is 8, so we'll have 8 times the square root of 10 is equal to 0. So let's solve for this. Let's move this over and divide by 6. So we'll have dx dt is equal to negative 8 times the square root of 10 over 6. Switch this over, divide by 6. And of course, this can be simplified a little bit more. So dx dt is equal to negative. Divide by 2 is going to give me 4. Square root of 10 over divide by 2 is going to give me 3. So just basically simplifying that fraction. So what unit am I going to have? dx dt is changing at this rate, but it's a velocity, and the unit is going to be meters per second. And how do I know it's meters per second? Because when I go back to my problem, dy dt was given in terms of meters per second, so my answer here is going to be in terms of the same velocity. So notice what this is saying. What this is really saying is if I put a 13-foot ladder against the wall and I take the top of it and pull it up at a speed of 1 meter per second, once this bottom scoots at exactly the moment where it's 3 meters from the wall, at that moment it will be going towards the wall at this value, 4 times the square root of 10 over 3. Why do you think we have a negative sign there? In calculus and in physics, which these are really physics problems, the negatives mean something. Don't just discard them. What it means is that, we define this in terms of x. Positive x is going this way. So if we had a positive value for dx dt, it means that dx dt would be getting bigger. X would be getting bigger as time goes on. But since we have a negative sign, it means that this distance x is getting smaller as time goes on. So all it means is it's approaching the wall. You see, we knew it was going to approach the wall from common sense. When you pull this up, it's going to scoot to the wall. But mathematically, it all worked itself out. So the value we got had a negative sign wrapped into it. That tells you that it's approaching the wall towards negative x, in other words. If it were getting bigger, it would be positive dx dt. If it's shrinking, it's going to be negative dx dt. And that's what happens there. Okay. That is a good introduction to related rates. I wanted to give you a good pep talk in the beginning to let you know that nobody's born knowing how to solve these problems. Nobody's born knowing how to read these things and totally set them up the first time. It takes practice. So the most important thing you can do for yourself is draw some diagrams. Then you need to write down the variables that are given to you in the problem. Then you need to have an equation of some kind so that you can take the derivative and plug in what you know. That's basically the recipe for all of these problems. When it's spheres and cubes and geometric shapes, then you know from geometry what the formulas are going to be. But a lot of times you're going to have to pull it yourself out to figure out what equation can I use to relate these things together so I can take the derivative and plug the things in. These first three problems were very good starter problems. Definitely good. You'll probably have something like that on your test. But they're a little more on the elementary side, right? Just to get your feet wet so you know what you're doing. We're going to have a ton of additional problems in the next section and the section after that just to give you some more related rate problems, give you more practice. Because the more you see of them, the better and better you'll get at them, the better confidence you'll have. So do yourself a favor, pause this video, work all of these out yourself, make sure you can get them all by yourself, and work some additional problems in your book, and then go on to the next section and we'll work some additional related rate problems. Increase the complexity just a little bit, but the basic recipe is going to be the same for all of them.